Great. So we'll start today's session. We were talking about last time, when a Taylor series represents the function. So when is it that f of x equals its power series or its Taylor series, i.e. f of x, is it equal or not to this, the Taylor series centered at A. And we saw that the answer to this is when we can show that the remainder is 0. So the way to answer this question is answer when the remainder approaches 0 when n goes to infinity. And we showed an example for the function e to the x, and we're gonna kick off this today's lecture by doing another example. This is when the function is cosine. So let me show you the page in the book. So the page in the book for this is, where's my book? Okay, so we're going to do this example. No, we did this one already, example 7. So now we're gonna do example 8. So that's the next page right here. Example 8. Show that the Maclaurin series for cosine x, which is that one, right? We have discovered that one before, actually converges to the function cosine x for every x between negative infinity and infinity. All right, so let's do that. And the way we're gonna do it again is by looking at the remainder. So example 8. Okay, so let's switch to the paper. And all right, so how do we do this? Well, we need to write down the expression for the remainder, right? So what is the remainder? So let's recall that the remainder is given by the following expression. Is exactly almost like this formula over here, the formula for the Taylor series, but instead of k, we use the next term. We use n plus 1. So the remainder is the n plus 1 derivative at some point c, that's the difference. And in this case, because we're doing cosine center at 0, this will be x to the n plus 1 over n plus 1 factorial. Right? So right now, remember, we're working with the function cosine x, and we're trying to show that its Taylor series equals a function. So the Taylor series for cosine x, let me write it right here. This is not needed for this problem, by the way, but I will just write it. The Taylor series is this one, is this negative 1 to the k x to the 2k over 2k factorial from 0 to infinity. You remember when we did it, the derivatives alternated, and they were 1, 0, negative 1, 0, 1, 0, negative 1, 0. So this is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, etc. Keeps going on like that, alternating signs. All right? Okay, so let's write down the expression for this remainder, right? So for that, we need to know the derivatives. And we've done this before, so let's just write them here. So if we've done this before, so if we do at least where this is k, and here we're gonna write the k derivatives. and plug in 0, we know that it's periodic of period 4. So after 4 iterations, it repeats. We start with cosine x. Then the derivative of cosine x is negative sine x. Then negative cosine x. And then sine. And when we plug 0, we get 1, 0, negative 1, 0. Right? That's where we did it. But right now, see, we're not plugging 0 here. We're plugging some number c, right? This number c is between 0 and x. So we don't really know that number c, right? So let's see if we can bound this expression. So we put absolute value to bound it because we don't care if it's positive or negative. We just want to know how big it is. So this remainder is the absolute value of the n plus 1 derivative at c times x to the n plus 1 over n plus 1 factorial. Right? And like we said, what is the n plus 1 derivative? Well, it's got to be one of these, right? Cosine, negative cosine, or sine. One of those 4, right? And here's the thing. Regardless of which one it is, when we plug the number c, we know that either sine or cosine, all of those are bounded by 1. They are at most 1. So let me write it here. So regardless of what fn plus 1 of c is, it could be cosine c, it could be negative sine c, it could be negative cosine c, or it could be sine c. Doesn't matter which one it is, we know that it's going to be at most 1 in absolute value. Is that clear? So remember, both sine, cosine, negative cosine, all of those are always between negative 1 and 1, right? Bounded between negative 1 and 1. So when you do the absolute value, it's at most 1, right? So therefore, the remainder is going to be at most, so this part is at most 1, so it's going to be at most x to the n plus 1 over n plus 1 factorial, right? And then we're essentially done because last time you may remember we did it for e to the x. We showed that the limit of this when n goes to infinity is 0. And we did it with the divergence test. Okay, so here the end is finally the limit when n goes to infinity of x to the n plus 1 over n plus 1 factorial is 0. And why is this? By the divergence test. So by the divergence test, because this series, the series x to the n plus 1 over n plus 1 factorial from n equals negative 0 to infinity converges for all x. And because it converges for all x, we know that then the term has to go to 0, right? Because if this was not, if the limit of this wasn't 0, that's the way we usually use the divergence test. If the limit of this is not 0, then this would be divergent. But it is not divergent, it is convergent, therefore the limit of this has to be 0, right? And if the limit is 0, then the remainder is 0, right? Because the remainder is less than this. So thus the limit of the remainder when n goes to infinity is 0, right? Because it's bounded by 0. This one goes to 0, and this one is smaller than that one, but positive. So it has to be 0 as well. And that's it. That's how we show the power series for cosine x also converges to cosine x. All right. Now, I was telling you last time that in practice, this is really generally difficult. So if I were to ask you to do this for every function that we're going to be working with, you're going to find that difficult. So the good news is you don't need to do that. So all the important Taylor series we've done so far have the property of being equal to the function. So that's what I'm talking about is e to the x, sine, cosine, ln of 1 minus x, ln of 1 plus x, arctangent, all of those, the geometric series, all of them happen to be the same as their Taylor series. So the function equals the Taylor series when the Taylor series is convergent. All right? So let me show you now then a summary of all of these important power series. So we mentioned this at the end of last class. So if you take a look at page 740, we'll find all the ones that we should know, right? All of these power series are relevant and be important because you use them to get other ones. They're like your basic library of power series, right? You can see them right here. So starting with the right here on top, that's the geometric series, 1 over 1 minus x. That one converges when absolute value of x is less than 1. Then we have what happens when instead of negative x, we put positive x, right? And we know that that's easy. You just make it with y, and we set y negative x. And when you do that, you get this alternating one, which also works when absolute value of x is less than 1. Then we have the exponential one, e to the x. Now, this e to the x one is good for all real numbers. That's fantastic. And you should memorize it. It's super useful, and we use it all the time. So it's x to the k over k factorial. We also have sine and cosine. Now, we didn't do sine, actually. We only did cosine. So take a look at cosine. And a really, really easy way to get the one for sine, instead of doing, you know, the Taylor series, finding all the derivatives, plugging the numbers, then getting the radius of convergence, etc. The better way is to just take the derivative of this one, right? So let me just do that briefly. So the question is how to quickly get the Taylor series for sine x. Given that we already know the one for cosine. All right. So let me show you how we can do that. It will be actually quite straightforward. So here's how we do it. What is the one for cosine? Here's the one for cosine. Cosine x is this one, negative 1 to the k plus 1 x to the 2k over 2k factorial from 0 to infinity. So this is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, etc. And we just checked that this is convergent for every x between negative infinity and infinity, right? We've checked this before. So how can we get then sine out of cosine, right? How are sine and cosine related? Anyone? with a simple operation. Taking the derivative, that's right. Gerardo, Michael, Ben, or others that replied. That's right. So we could take the derivative of this, right? So we and multiply by -1. So if we do the derivative, it will be negative sign. But then we simply should multiply by -1, and then we get it, right? And we know that when we take the derivative, the radius of convergence stays the same. So we don't need to do that extra work. Here we already know that R is infinity. This is good for all real numbers. So then let's take the derivative. So we take the derivative of cosine, and that's going to be negative sine. And then you simply take the derivative of this one, right? So let's see, the derivative of 1, that's 0. Then the derivative of negative x squared over 2 factorial, that will be negative 2x over 2 factorial. Then the derivative of of x to the 4th, that will be 4x cubed over 4 factorial minus 6x to the 5th over 5 factorial plus 8x to the 7th over 8 factorial minus etc. Right? So the next one will be 10x to the 9 over 9 factorial, etc. And you can appreciate already that what's going to happen is these 4. So what is 4 over 4 factorial? Or let's see, this is a little mistake here, right? That's 6. This should be 6 factorial. And this should be 10 factorial. I was in my head already simplifying. So yes, so what is this 6 over 6 factorial? Where 6 factorial is 2 times 3 times 4 times 5 times 6, right? So for example here, 6 over 6 factorial, that's the same as 6 over 1 times 2 times 3 times 4 times 5 times 6. So it means cancel the last one, right? So this 6 cancels that 6, and where you're left off is 1 times 2 times 3 times 4 times 5, meaning 5 factorial, right? So this thing simplifies as negative sine x equals negative x plus x cubed over 3 factorial minus x to the 5 over 5 factorial plus x to the 7 over 7 factorial minus x to the 9 over 9 factorial, etc. And now to get the one we want, we simply multiply by -1, right? So here's the one we want. Sine x is actually x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial, etc. In general, it is -1 to the k plus 1 x to the 2k plus 1 divided by 2k plus 1 factorial, starting at 0 and going to infinity. And this is good for any number between -infinity and infinity, right? Just as the one we had for cosine was true for all. Just as the one for cosine was true for every x, this one for sine is also true for every x. Notice the nice pattern, right? The one for cosine, let me put it back, has starts with positive, and it alternates with the even numbers, 2, 4, 6, 8, right? Are the exponents here. And in the denominators, the corresponding factorials, 2 factorial, 4 factorial, 6 factorial, 8 factorial. Well, the one for sine has the similar pattern, but with the odd numbers. So it goes 1, 3, 5, 7, 9. It alternates signs, starting with positive, positive, negative, positive, negative, positive, negative. And the factorials in the bottom correspond to the exponents. So 3 factorial, 5 factorial, 7 factorial, 9 factorial. All right, so that's an easy way to get the one for sine x. Let me go back to the list that we had from the book. So we did sine, cosine. We have this ln and negative ln that we done a couple of classes before, not as Taylor series, but starting from the geometric series, we figured those out. and they have to be the Taylor series because the power series is unique. Then we have arctangent, which we also did in a creative way. So we started with the geometric series, then we substituted y equals negative x squared to get 1 over 1 plus x squared, and then we integrated that to get arctangent, and that's how we obtained this one over here. Observe that the pattern is also the odd numbers, but you can compare with sine. It looks a lot like sine, except sine has factorials in the bottom, and this one does not have factorials. It's just the numbers 1, 3, 5, etc. as the denominators. All right. Then pay no attention to this sine hyperbolic and cosine hyperbolic. We don't do those functions. And the last one you should know is the one we did at the end of last week, the binomial Taylor series, right? So I'm not going to go over it again. I just want to make you aware of its existence. All right. So that's all I wanted to do about this section 11.3. So now we can go into the next one, which is working with Taylor series. So why are Taylor series good? How are they helpful, right? And we talked about this. So now we have different ways of portraying the same function. Like we can write sine or cosine or e to the x in a different way that is maybe sometimes better for purposes of, you know, calculating an integral or maybe evaluating a limit. And we'll see some examples about that. So this will now start section 11.4. And these are working with Taylor series, right? So 11.4. And we'll go right away and start working on the examples. So we'll start with example 1. So here's example 1. In fact, since I have the book right here, maybe we'll put it on the screen. This is now from page 742. And it's about calculating a limit, all right? Now, this is a limit that we can do in a different way, but we'll do it using our new properties. So it says a limit by Taylor series. Evaluate this limit over here. X squared plus 2 cosine x minus 2 over 3x to the 4. Now, this is one of those limits where you could use L'Hopital's rule if you wanted to, right? The problem is you're going to have to apply L'Hopital's rule several times, right? And in this case, not that many times. It's only going to be, I think, 4 times. We need to apply L'Hopital's rule 4 times. But you can see how I could make this problem difficult, right? I mean, I could modify this problem and make it so that if you use L'Hopital's rule, you need to do L'Hopital's rule 20 times. And then you don't want to do it that way, right? Then maybe you want to do it the way I'm going to show it to you right now. So the question is calculating this limit. The limit when x approaches 0 of x squared plus 2 cosine x minus 2 divided by 3x to the 4th. Now, immediately you know that this is 0 over 0, right? If we plug 0, we get 2 cosine 0, that's 2. And so you get 2 minus 2 is 0. So the top is 0 and the bottom is 0. So it's definitely one of those harder limits. All right? So let's go back to the page and I'll show you how we can do it with our new knowledge about power series, right? So the idea, of course, is to replace cosine x by its power series. So I'll write it here. Cosine x, remember, we just saw it, is this series, is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, etc. More terms, right? Now, let's create this expression, right? So let's multiply this by 2 and add x squared minus 2 and then divide everything by 3x to the 4th, right? In other words, create the expression for the limit, okay? So I'll do it here. So first, x squared minus 2 plus 2 cosine x. All right, so I'm just going to write x squared minus 2 and then multiply this by 2. the expression that we have on the top by 2. So all of these times 2. So it will be plus 2 minus 2x squared over 2 factorial plus 2x to the 4 over 4 factorial minus 2x to the 6 over 6 factorial, etc. Right? Okay. Next, we need to divide by 3x to the 4th, everything. But first, maybe we should arrange this, right? Simplify it the way it should be simplified. So you can observe, for example, that this negative 2 and the 2 are going to cancel. And so will this x squared and this negative 2x squared over 2 factorial, because 2 factorial is 2, right? So this is also negative x squared. So this negative x squared cancels x squared. So all we have left is the following, is 2x to the 4th over 4 factorial, that's 24 by the way, minus 2x to the 6 over 6 factorial plus 2x to the 8 over 8 factorial minus 2x to the 10th over 10 factorial, etc. Notice that I'm not paying attention to these other factorials and don't want to expand them, because I know already that the only term that's going to matter is this 3x to the 4. All right, so now we divide by 3x to the 4th and we calculate the limit. So it's the limit when x approaches 0 of x squared minus 2 plus 2 cosine x divided by 3x to the 4th. Well, that's like this expression, but divided by 3x to the 4th. So it's 1 over 3x to the 4th. Oh, don't forget the limit like I just did right now. 1 over 3x to the 4th times all of these, which is x to the 4th over 12 minus 2x to the 6 over 6 factorial plus 2x to the 8 over 8 factorial minus 2x to the 10th over 10 factorial, etc. Right? Now, look at the limit we have. Now it's an easy limit, even though it's a series, right? Even though it's a series, it's an easy limit because x approaches 0. So we're going to substitute 0 for many of these things, right? And right now, we can't do it because we're dividing by 0. But if we multiply this term by each one of these, it's going to simplify. Look, this will be, see, x to the 4th and x to the 4th, they go away. So it's 1 over 36, 3 times 12, minus, then is 2x squared, right? 6, power 6, power 4 simplifies to second power, divided by 3 times 6 factorial, plus 2x to the 4th. Now it's x to the 8th and x to the 4th becomes x to the 4th. And it is 3 times 8 factorial, minus 2x to the 6, 3 times 10 factorial, plus, etc. Right? Okay, and now here's the beauty of it, right? We're plugging 0, and that's why I didn't even multiply this out. Why? Because I don't need it, right? I'm gonna now make the limit when x approaches 0. So all of these guys go away. They're all going to 0. The only thing that survives is this 1 over 36. And that's the answer to my problem. All right? Questions? All right, so that's just one such example. There's example 2 is done in a similar way, although it has a little bit of an additional restriction, so maybe it will be interesting for us to check it out. So let's do example 2. So it's on the next page, and I'll just write it here, example 2. So this time we need to do the limit when x goes to infinity of 6x to the 5th sine of 1 over x minus 6x to the 4th plus x squared. All right, Now, this one is challenging. Even if I let you use L'Hopital's rule, you will find it a difficult problem because it's not clear what we have, right? I mean, think about it. This guy goes to negative infinity, but this guy goes to infinity. Now, it seems like this guy is pushing harder because he's x to the fourth. But then you also have this guy that we don't quite know what it does, right? X to the fifth goes to infinity, but this goes to zero. So it's like infinity times zero. So who knows, right? It depends which of the function is pushing the hardest. So this is actually a very difficult limit. Now, there is an additional trick before we can use the Taylor series, and it is that 1 over x is complicated, right? You don't want to do the Taylor series of sine x and then plug 1 over x, because then you're going to have an expression with a lot of things in the denominator. The better trick here is to do a change of variable, kind of like a u substitution for the limit. So the better thing here is to replace 1 over x by a new variable. Let's call it t. So t will be 1 over x, right? And then what happens when x goes to infinity? So when x goes to infinity, t goes to where? So if this is really, really big and positive, that's right, Gerardo, thank you. It goes to 0, and Michael, right? T goes to 0. And more important, it goes to 0 from the right, with positive numbers, right? We don't have any negative numbers because this will be a positive fraction. So t goes to 0. That's right. So let's now change this limit. So the limit becomes the limit when t goes to 0 from the right. And then we need to replace everything, right? So instead of x to the fifth, so if t is 1 over x, what is x? Well, x is 1 over t, right? So this is 6 times 1 over t to the fifth sine t minus 6 times 1 over t to the fourth plus 1 over t squared. Is that right? Okay. So now let's simplify this expression and then substitute the value of sine, right, according to its Taylor series or power series in general. So here we go. Okay, so our limit is now 6 sine t over t to the fifth minus 6 over t to the fourth plus 1 over t squared, right? I just simplify this. And now I'm gonna plug what sine t stands for. So what does sine t stand for according to its Taylor series centered at 0? Well, it is t minus t cubed over 3 factorial plus t to the fifth over 5 factorial minus t to the 7 over 7 factorial, etc. Right? And this is good for any t. So I can freely substitute it here. So I can multiply it now by 6 and divide by t to the fifth and see what happens. So this one will be multiplied by 6, 6t, and divide by t to the fifth, minus 6t cubed, and divide by t to the fifth. So 3 factorial t to the fifth, plus 6t to the fifth, 5 factorial t to the fifth, minus 6t to the 7, 7 factorial t to the fifth, plus, let me do one more, 6t to the 9, 9 factorial t to the fifth, minus, etc. Right? Okay, let's simplify it. This will be 6 over t to the fourth. This will be 3 factorial is 6, by the way. So these two cancel, right? 3 factorial is 2 times 1 times 2 times 3, so that's 6. So these two cancel, and simplifying the exponents here gives me 1 over t squared. Then here the t factorials go away, and what I have is 6 over 5 factorial, which is 120. Then I have 6 t squared over 7 factorial, 6 t to the fourth over 9 factorial, and etc. Minus the next ones will be like this, 11 factorial, and more. All right, and now you can tell, right? I mean, let's go back to what the limit we wanted to do was, right? We want to do this limit over here. So I have this expression, which is this, and then I was gonna subtract these two. Oh, that's easy because look, they just appear right here, right? So I just gotta put them on the other side of the equation. So let's do that, and then take the limit. So let's write down the limit that we want, which is 6 sine t over t to the fifth minus 6 over t to the fourth plus 1 over t squared. Well, that's the same as the limit when t approaches 0 of, remember, we move this to the other side of the equality, so we only get this other stuff, right? 6 over 120, that is 1 over 20, minus 6t squared over 7 factorial plus 6t to the fourth over 9 factorial minus 6t to the 6 over 11 factorial, etc. The important here to note here is that all of these terms, starting from the second, all of them are t to the something, right? T squared, t to the fourth, t to the sixth, t to the eighth, t to the 10th, etc. So what's going to happen when we let t go to 0? When t goes to 0, what's going to happen to all of these guys? Yeah, they're all going to vanish, right? They're going to become 0, right? So these, all of them will go to 0. And that's how we can get the answer to our limit, is 1 over 20. All right? Questions? All right. Now let's see what other applications we have in this section 11.4. We have example 3, which is something we already did. So there's no need for us to do that one. I'll show it to you on the screen. And I think it's at the bottom. Yes. So right here, the problem is differentiate the Maclaurin series for sine x to verify that the derivative of sine is cosine. Well, we sort of did that, right? To discover the one for sine, we took the derivative of cosine. We could instead have integrated. That was another way to go, right? Maybe we wanted to integrate cosine to get sine. We could have done that too. That would have been a different way of getting the one for sine. So I'm going to skip that one. And instead, I'm going to look at example 4 on next page. Let's take a look at example 4 on next page. Okay, so let's do this example 4 question. It says, it's about a differential equation. So it says, find a power series solution of the differential equation y prime equals y plus 2, subject to the initial condition y of 0 equals 6. And then it says, identify the function represented by the power series. All right, so differential equation, in case you've never heard that term, is just a fancy word for saying we want to find a function that satisfies some properties, right? And so we need to find the function y. Find y, and we have 2 clues. Find y such that 2 clues. One of them is that y prime is the same as y plus 2. So the derivative of y is almost the same as y. It's not quite the same. It's the same as y plus 2 units. And we also have an initial condition, which is that y of 0 is 6, right? And y of 0 is 6. I'll switch to the page and we'll work it out. So how do we work it out? Well, so this is what we need to do. And the way to work it out, I mean, there's techniques. In fact, we have an entire class devoted to finding differential equations. So there are other techniques, but using what we have learned, what we can do is assume that this function y has some power series, right? And try to come up with the coefficients. So some power series centered at 0. So suppose that y of t is given by some power series, ck t to the k, from 0 to infinity. So all we need to do is find these coefficients. What are these c's, right? Find the c's is what we need to do. Find the ck's. Okay, now how do we do it? Well, we can use the fact that it's really easy to take the derivatives of power series, and that when you take the derivative of power series, we have another power series that is also valid. So what would be y prime? Well, all we need to do is take the derivatives here, right? So the k comes down, multiplies the ck. Well, when k is 0, it's a constant, and the derivative of constant goes away. So this one is going to start at 1. And then the k comes down, multiply ck, and we subtract 1 to the exponent. Right? That's the derivative. Now, let's do the j substitution so that it starts at the same as the original one. So then let's make j k minus 1. So then this looks like j plus 1, c j plus 1, t to the j, from this time from 0 to infinity, right? And we're doing this so that I can compare these two. Because what do we know? We know that y prime is y plus 2. So this power series, when we add 2 units, should be the same as that one. Is that clear? So let's add 2 units. So what is y prime plus 2? Well, is going to be c. So let me write the 2, and then let me expand the terms of this one, right? So let's write this one down. So this one starts at 0. So when it is 0, this is 1 times c1. So c1 times t to the 0. Then plus, the next one is when j equals 1. So that will be 2 c1, I mean c2, my bad, 2 c2t. Then is 3 c3 t squared, 4 c4 t cubed, 5 c5 t to the 4th, etc. Correct? That's y prime plus 2. Now I'm going to write down y in the bottom so that you can compare them. So here's y. Y is c0 plus c1t plus c2t squared plus c3t cubed plus c4t to the 4th. And notice how I space this one weird. Why am I spacing it weird? Well, because since these two are the same, then these numbers have to be the same. This one has to be the same as C1. This one has to be the same as C2. This one has to be the same as C3, etc. Right? Starting with this. 2 plus C1 has to be the same as C2. And one additional thing that we haven't used, y of 0 equals 6, right? So what happens here when we plug 0? Well, we know it's 6, but when we plug 0, all of these terms be canceled, right? C1t cancels, C2t squared cancels, C3t cubed, all of these cancels except C0. So I know now what C0 is. Yeah? So now we're like detectives. We're figuring out with our clues, we need to figure out all the C's. And we already got one. C0 is 6. Now I guess that with this one, we can figure out C1, right? Let me get more paper here. And we'll move it along. How? Well, we know C0. C0 is 6. And we know 2 plus C1 is C0. But this one is 6. So then I know C1, right? C1 is 4. Yes? Now the next. Now I go to the next one over here. I know that 2C2 is C1. But C1 is 4. So then what is C2? Well, is 2, right? And then we go to this one. 3C3 is C2, which is 2. So then what is C3? 2/3, right? Then we go to the next one. 4C4 is C3, and C3 is 2/3. What is C4? Well, is 2 over 3 times 4. So that's 1/6. Actually, better if we don't simplify it here so we can look with a pattern, right? So this 4 is actually 4 divided by 2. This 2/3 is actually the one we had before, which was 4 divided by 2 times 3. This one is 4 divided by 2 times 3 times 4. If you leave them like that, you'll recognize the pattern in an easier way. So let me do one more. The next one says that 5c to the 5 is C4. And C4 we know is this one, is 4 divided by 2 times 3 times 4. So then to get C5, all I need to do is divide by 5. So it will be 4 divided by 2 times 3 times 4 times 5, right? Or in other words, 4 over 5 factorial, right? This is 4 over 4 factorial. This is 4 over 3 factorial. This is 4 over 2 factorial. And this is 4 over 1 factorial. That's great. I think we figured out the pattern, right? So let's do one more and then just write down the pattern. So let's check if it works. The next one would be 6C6 is C5. Well, we know that C5 is 4 over 5 factorial, right? From here. So then C6 should be 4 over 5 factorial times 6. But if you take 5 factorial and you multiply by 6, that becomes 6 factorial. Great, the pattern works, right? So what do we think is going to be CK? The pattern says that CK will be 4 over K factorial, right? Okay, and that's great. Believe it or not, we've got now our function. What is our function? Our answer to our differential equation. Well, here it is. I mean, maybe you don't like this answer because it's a series, but it is the answer to the problem. The problem, we wrote it as a Taylor series, and now we know what the C is. So this is just 4 over K factorial T to the K, right? We got it. That's what it is. That's the answer. And that's a perfectly reasonable answer. I mean, it's just not a way in which you usually present functions, right? You would like to say, oh, the answer is sine t. or the answer is t squared or t to the fourth? Well, this is a series, and as a series, it is the answer to our problem. Now, the last part of this problem actually does says a little extra. It says, and then recognize what the answer is. Let me look at the wording. It says, identify the function represented by the power series. Identify the function. Okay, well, we can't do that because take the 4 out. And then what you get is, hold on a second, actually, let's see, C0 was different, right? Let me backtrack a little bit. This is not quite right. It's almost right. So I just messed up. So let's go back to our C's. So our initial C was C0, which is 6. So that's a little bit different, right? But then after that, they are all 4 over k factorial. So this is, I should write it more precisely. It starts at 1. And this is 6 plus. So the first term is 6, and then you do these ones over here, right? Now I'm still gonna do what I was telling you to do. I'm gonna take this 4 out. So I'm gonna take the 4 out of the expression. So it will be 1 to infinity t to the k over k factorial. And it doesn't start at 0. That bothers me a little bit. So I'm gonna put the 0 term. If I put the 0 term, it would be 4 times 1. So I'm gonna borrow 4 units out of this 6. So take 4 units out of this 6. So write it as 2. And then leave the other stuff here so that it can start at 0. And the reason I'm doing this is because you should recognize what this is. What is this? What is this Taylor series? Remember, it's one of those that I told you should know because it appears all over the place. Well, so what is the power series? Yes, correct. Somebody already answered, right? Actually, the variable is not x, Gerardo, but other than that, you're right. So that power series from 0 to infinity, that is t to the k over k factorial, is actually e to the t. That's correct. So this expression is e to the t. So we actually can write our function in a compact way. Is this one, 2 plus 4 times e to the t. That's the answer to our differential equation. Let's check it just for the sake of it, right? So what is y of 0? When we do 0, it would be 2 plus 4 e to the 0, and that's 6. Nice. So y of 0 is 6. And then what's the derivative? Well, the derivative of 2 is nothing, and the derivative of 4e to the t is 4e to the t. And that happens to be the same as y minus 2, correct? And that was the problem we wanted to solve originally, right? So the derivative of y prime was we wanted, hold on a second, didn't we want y plus 2? Did we wanted y plus 2 or y minus 2? Let's check. Maybe oh, okay, I messed it up a little bit at the beginning. All right, my bad. So I did a slightly different problem. Let me show it to you because I calculated y prime plus 2 and I made these two the same. So I did a slightly different problem. Instead of doing this one, that y prime equals y plus 2, we didn't do that one. We did a different one. We didn't do this one. The one we did was y equals y prime plus 2. Okay, my bad. But the other one is solved the same way, all right? I don't want to replace that little thing because then it's gonna affect all the other terms. but it's done the same way. All right. So our function satisfies this differential equation. Is that y prime is y minus 2, or y equals y prime plus 2. Okay, so that's the one that I used. Y equals y prime plus 2. All right. Questions? All right. Just
Professor,
yes.
I have a question. How, or could you explain again how 2 plus C1 goes to C0 and 2C2 goes to C1, etc.?
Yes, absolutely. So let's go back to this part over here, right? So remember, we're not doing this anymore. So we're doing this, y equals y prime plus 2. So here's what I did. I first calculated the derivative, right? So to calculate the derivative, you just take the derivative of the terms. So the k exponent comes down, multiplies the coefficient, and subtract 1 to the exponent. So here's the derivative when you add 2. So the derivative plus 2. So here's the 2, and then here's the derivative, right? It's c1, 2c2t, 3c3t squared, 4c to the 4t cubed, 5c to the 5t to the 4th, etc. Right? And then to figure out the equations that you're asking about, I'm using the condition that these two have to be the same. Y prime plus 2, this one, has to be the same as y. Here's the coefficients for y, c0, c1t, c2t squared, c3t cubed, c to the 4t to the 4th. So when two Taylor series are the same, the only way two Taylor series are the same is if every coefficient is the same. So the independent term has to be the same. The coefficient for t has to be the same. The coefficient for t squared has to be the same. The coefficient for t cubed has to be the same. All of them have to be the same. So what is the independent term? Here is 2 plus c1. What is the independent term here is c0. So then I have that 2 plus c1 has to be c0, right? Now c0, we figured it out from the from the initial condition. So the initial condition was that when you plug 0, you get 6. So when you plug 0, everything here cancels. So except C0. So C0 then has to be 6. That's how we figure C0. Then, for the others, look, C1 has to be the same as 2C2. That's the one that's written here. 3C3 has to be the same as C2. That's the one written here. 4C to the 4 has to be the same as C3. That's the one written here, etc. Right? So in general, 5c to the 5 has to be c4, and k c to the k has to be ck minus 1. All right? And then we started with c0, and knowing c0, we plug it to find c1. Knowing c1, you plug it to find c2. Once you know c2, you plug it here to find c3. Once you know c3, you plug it here to get c4, etc. All right? And in general, you find all of them, and here's the expression. Does that answer your question, Michael?
Yeah.
Good. All right. It's already 12:06, so I'm going to stop right here. We'll continue with the other problems on this section next week. I mean, not next week, next class. What I meant to say is that remember tomorrow we won't meet. This is Cesar Chavez Day. So we'll continue on Wednesday. All right? Be aware of that. Any other questions?
Oh, I have one more question.
Shoot.
So, it's for the I think it's the power series, or it was a problem we did earlier when we took the limit of and we used the divergence test to show that it equals 0.
Correct.
So, and then we said it was convergent. Isn't it when it equals 0, it's inconclusive, or am I getting mixed up?
No, you are correct. So in general, we use that statement in a different way. So here's let me write the divergence test and then explain that point to you. Yeah, because it's a subtle point indeed. So so here's the divergence test, the way you know it, right? If you have a series, you have a series, right? Some series, and then you say if the limit is not 0, then the series diverges. Correct? Is that the way you understand the divergence test, Michael?
Yeah.
Okay. Now, imagine now the opposite. That's actually the way we prove it, by the way. If you go back to the book and you read when we explain why this happened, we did it the other way around. So here's the opposite. So what happens if this doesn't happen, right? So it's like if it's raining, there are clouds in the sky, yeah? So the contrapositive of that is if there are no clouds in the sky, then it's not raining, right?
Mm-hmm.
So the contrapositive of this statement, logically speaking, is that if this one does not diverge, if this doesn't happen, then this doesn't happen, right?
Yeah. So it has to equal 0.
Correct. And does not diverge is the same as converge, right? So that's a property we actually know, that every time you have a convergent series, the terms have to go to 0. That's how we used it. So let me now show back to you the problem where we used that. It was at the very beginning when we were showing that the remainder goes to 0, right here. So for this problem, right? So we had, no, not this one, this one. We use the fact that this limit is 0, and we wanted to show this limit is 0. And the way we did it is because we know this one converges. And how do we know this one converges? Because that's the power series for e to the x, right? This is like e to the absolute value of x. So that's because we know this one convergence, then this limit has to be 0. That's how we used it.
Okay.
Good. Anything else? Okay. So like I was telling you guys, we'll continue not tomorrow, but the day after. Stay safe, everyone, and I'll see you in a couple of days.